Hi everybody. So on this video we're going to focus on chaos applications again. We are going to discuss false attractors and their applications in random bit generator and other types of security. Okay, so the topic of today's video comes from our recent publication in Physica Scripta. It's called false strange attractors as sources of pseudo randomness. Okay, so this PDF is open access. I'm going to put a link in the description of the video so you can download it and read it. And moreover, I'm going to put a link on MATLAB code to simulate your own false attractors. Okay, so you can experiment with this technique yourself. Okay, so let's talk about attractors. Okay, probably you already know what an attractor is. Basically, we have a nonlinear system. We solve it. Okay, we obtain using some numerical technique the solution as a time series. Okay, for each individual state. For example, for the Lorentz system, we have the solution for x1, x2, and x3. Okay, so we can either plot all of these solutions with respect to time, or we can plot these solutions x1, x2, x3 with respect to each other, as you see right here in this graph. And this gives us the so-called phase portraits. Either we can plot them as pairs, x1 with x2, x2 with x3, x3 with the x2, or we can plot them all of these three states together and obtain the 3D phase diagram that you see on the left. So another name for this phase diagram, of course, is a chaotic attractor or a strange attractor. Okay, so you are probably familiar with this concept. Now, let's say that I have the solution of the system for all three states, and I have saved all of these states in a single vector. Actually, it's not a vector, I'm sorry, in a single matrix. So we have a matrix with three rows. The first row is the solution x1, the second row is the solution x2, the third row is the solution x3. Okay, so this is just a matrix with the values for the solution. Okay, so this is a classic attractor. So what's a false attractor? A false attractor comes from a very recent paper, let me show it right here, by Rezend and Boali, I hope I'm pronouncing this correctly, discovering the beauty of false strange attractors from 2021. Okay, so we took this paper and we made some changes in how the false attractors are computed. We made some changes for efficiency and also some generalization. So what is a false attractor? The idea the authors proposed is this, that we take the original time series and perform some delays in each individual state. So for example, let's say I take the first state and I transpose it in time, which we propose doing through circular shifting, which is highly efficient in MATLAB. Okay, so we add a delay and we circular shift the first state by some value. We do the same thing on the second state and on the third state. Okay, so if I do this circular shifting, which is equivalent to adding some delay in each individual state, basically I get a shifting matrix where if I were to plot pairs of states now as an attractor, we won't have x1, x2, and x3 over time p. We will have x1, x2, and x3 over different times. Okay, so if I plot these time series, which are now shifted, in time, I'm going to get a shape which is basically like an attractor, but actually it doesn't represent the solution of a system because it represents the solution after a artificial shifting in the states has been performed. So basically what I'm seeing in the state space, I'm going to show you some graphs, is not an actual attractor. It is a false attractor. And by false, we mean that it doesn't actually represent the solution of a system. Okay, it represents the result after we perform this artificial shifting on the solution of the system. Okay, hence the term false attractor. Now, we made some changes and described a bit more analytically how we can compute exactly the false attractors. And we made some changes for efficiency because we have in mind encryption, actually, for these attractors. And we also performed the generalization. So after we perform this shifting and we have this matrix Z, we actually multiply this matrix Z by a matrix P, which is a so-called elementary matrix. Now, I can assume that you've all had some course in linear algebra. And you remember when we say elementary operations, we basically mean three individual basic operations performed on matrices. So either we have some shifting on the rows of the matrix, first elementary operation. We have multiplication of a row by a specific element, okay, by a scalar. So this is the second elementary operation. And the third elementary operation is that we multiply a row by a number and add it to another row. Okay, so we can add any possible combination of elementary operations into this matrix Z that represents the false attractor. Okay, so as you know, each elementary operation is represented by a matrix, and all of these matrices can be combined into a single matrix P. So P right here represents any amount of elementary operations that we perform on the false matrix representing the false attractor. Okay, and with this addition, we basically generalize the notion of what a false attractor can be. Because apart from delaying, we also add elementary operations in the states. Okay. So why do we do that? The idea behind this is that starting from a single attractor for the chaotic system, we can now create a very big family of numerous different false attractors. Okay. And we can generate new false attractors at a very low execution cost because elementary operations and circular shifting are extremely fast in MATLAB, and actually they are extremely fast in other programming languages as well. So we do basically create numerous variations of the original attractor at a very low cost. Now, this is extremely useful in applications because in applications we can have a very increased efficiency by considering numerous different time series, starting from just one time series, the original solution. Okay, and this is very helpful for security or encryption applications, right? We basically increase the key space a lot if we are using the attractor in some sort of encryption application, because basically the amount of delaying and the elementary operations can all be part of the secret key. So we can have an encryption technique with a very increased key space. Okay. We can have a better key management, which, as you may know, is a problem in chaotic encryption. And basically, we have better key management because we have not any issues or any danger of falling into periodic behavior. Because if the original attractor is chaotic, any false attractor will also be chaotic. Apart from very small cases where we don't choose the matrix P properly, but we can easily avoid those cases. Okay, so we can have a much better key management. And our idea is to use these false attractors in encryption, but other applications as well. I'm going to discuss this a bit later. So these types of false attractors have a very big potential in any application of chaos. Okay, so there is a big promise here of many applications. Okay, and of course, apart from applications, remember that basically false attractors, the authors of the original work also commented on that. They basically constitute a mathematical object of beauty, as they say, but also a very interesting mathematical object. It can be used for further experimentation and studying, okay? For example, identification. I'm going to discuss this later. So let me show you some false attractors. You have already seen the original attractor for the Lorentz system. Now, this is an example of a false attractor on the Lorentz system that you saw earlier, on the Lorentz attractor. I have basically added a delay for the first state. I write it down here. So the first state is delayed by 80 values. Second and third state are the same. And the elementary matrix is the identity. Okay. So you see the new shape is completely different in the 3D space. In X2, X3, it's actually the same because I haven't changed those states. But in the 3D shape, is completely different to the original attractor, right? So it's an entirely new attractor. This is not a real solution from the Lorentz system. This is an artificial solution that resulted after I performed these operations that I described. Okay, so that's why we call this a false attractor. This is another example of a false attractor. I have again delayed the second and third states, and I also multiply by an elementary matrix, which I write down here below. Okay, so this is a new false attractor, completely different from the Lorentz in shape. Again, this is another false attractor. This kind of reminds us of the butterfly for the Lorentz because the delays I have are very low in value, 20 and 40 values only. And of course, I also have a non-identity elementary matrix. So again, you see a much different attractor than before. Okay. And you can actually do the same technique with any possible system. For example, here on the left, I have another paper that we considered in our work. And this is the original attractor on the left. But on the right, you see the false attractor again that results from this operation. So basically, you can take any system that you like and transform it in order to create false attractors. Now, as I said, false attractors have a very big potential in any application relevant to security or encryption. because as you may know, we often use chaotic attractors in applications relevant to security. For example, in random bit generators, in encryption, image text encryption, in substitution boxes, in authentication. And basically, with this technique, we can have a single attractor and create numerous variations of the attractor, okay, at a very low cost. So possibly all of these variations can be used to perform such actions related to security. And our goal, my goal, and our authors as co-authors as well, we want to explore other applications in the future. For example, I believe path planning will be a great application of false attractors. As you know, chaotic path planning is the idea where you generate chaotic trajectories for exploring a specific area, like a grid, for example. Okay, so it's a very, very, very good application of chaos. We have many papers there in the literature. And of course, another problem is identification, because as I told you, false attractors are actually artificial attractors. They don't represent solutions of any actual system. But through identification, it may be possible to actually create systems that have false attractors as solutions. We comment that on the full-length paper. This is a very interesting topic. I believe it has a lot of potential. Actually, all of these applications have a lot of potential. And I think in the future, we can actually think of more applications as well. Now, to persuade you that actually false attractors have applications, in our own paper, we consider an application to a random bit generator. As you know, these are very common in encryption. So what we did, we have a series of rules that generate 64 bits per iteration of the algorithm. And basically, for each of these 64 bits, we have a combination of the three states. So on the first rule, we add them. On the second rule, we multiply them. And we do this in order to have a very, very, very increased avalanche property. As you know, avalanche property is very useful in encryption and important in encryption. And through these operations, basically, any change in the false attractor results in a change in the prbg. Okay. So what we did is this. We considered this random bit generator, okay, through the original Lorenz attractor and through three different false attractors that all result from the original Lorenz system. So basically, we tested the NIST statistical tests, which are 15 statistical tests of randomness, for the original attractor and three false attractors. All of them passed the statistical tests successfully. This tells us basically that if the original attractor can be used as a bit generator, okay, a random bit generator, then all of the false attractors, if properly chosen, can also be used as random bit generators. So this is a very good proof that false attractors have a lot of potential in applications related to encryption. But as I told you, we want to explore other applications in the future, so I believe there is a lot of potential here. We'll see how it goes, but I'm very, very positive in exploring other applications as well. Okay, so thank you very much for your time. As I told you, you can find the MATLAB code and the full-length paper in the description of the video. Okay, so see you later.